Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems ISC. Today's talk is by Dr. Debdeep Mukhopadhyay, and he will be speaking on Every Contact Leaves a Trace, Side Channel and Microarchitectural Attacks on Modern Cryptosystems. Professor Debdeep Mukhopadhyay is currently a professor at the Department of CSC, IIT Kharagpur. At IIT Kharagpur, he initiated Secured Embedded Architecture Laboratory, focusing on hardware security. He had worked as visiting scientist at NTU Singapore, visiting associate professor of NYU Shanghai, assistant professor at IIT Madras, and visiting researcher at NYU London School of Engineering, USA. He holds a PhD, MS, and a BTech from IIT Kharagpur. His research interests are on the topics of cryptographic engineering and hardware security. Recently, he is intrigued by adversarial attacks on machine learning and encrypted computations. Professor Mukhopadhyay is the recipient of prestigious Shanti Swaroop Bhatnagar Award 2021 for Science and Technology and is a fellow of the Indian National Academy of Engineers. He was awarded the Qualcomm Faculty Award 2022, the Khosla National Award from IIT Roorkee 2021, DST Swarna Jayanti Fellowship 2015-16, INSA Young Scientist Award, INAE Young Engineer Award, and Associateship for the Indian Academy of Sciences. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Debdeep directly or type them in the chat box and we'll moderate it with him. Over to you, Professor.
So thank you very much for the kind introduction and also for inviting me to this talk series. So as announced, my talk is titled as Every Contact Leaves a Trace, Side Channel and Microarchitecture Attacks on Modern Systems. In this talk, I shall be trying to give an overview on side channel and microarchitectural attacks, and try to also talk about some of the recent works that we are doing in this context. So to begin with, so the overall topic of my work has been in the area of hardware security, which tries to bridge the gap between theory and practice. So we all know that. So this illustration kind of shows depicts the classic scenario of where there are two end parties like Alice and Bob who are communicating, and there is Eve or Mallory, an eavesdropper who is trying to observe the untrusted communication channel. So this is the classic overview on how cryptography works. We have got, the attacker always interested in the secret key. However, we all know that the cryptographic theory has limitations, and there is an absence of theory for the reality, because of which even mathematically strong ciphers can leak in the real world through unintentional information leakages, which are often called as side channels. So side channels in the real world has been quite a serious threat to even the strongest of cryptographic algorithms, because they are often not what the designers often anticipate. So to give a rough background behind my area of research, so I have been working in this domain of translating theoretical constructions of cryptographic algorithms into secure practical instances. So to kind of motivate this work of research, suppose we make a mathematical statement saying that G is a mathematical group where discrete log problem is hard. Now this is often a widely believed assumption based upon which several cryptographic algorithms have been constructed. However, in the real world, when you want to kind of develop a practical instance of a cryptographic algorithm, we also need to develop a practical instantiation for the same. And so when we go for a practical instantiation, then we often, like have this elliptic curve discrete log problem as a very promising candidate for such hard functions, based upon which we have got this, we have this world of public key cryptography, which are called as elliptic curve cryptosystems. However, the point that I would like to highlight is that there have been a plethora of attacks in the real world, which can actually break ECC without even trying to solve the ECDLP problem. So often, the ghost lies in the implementation, and because of which, right, there can be a lot of attacks on the crypto implementations, the crypto libraries, whether when we're talking about software or crypto accelerators when we're talking in the hardware domain. So my research has been largely in this translation of, of theoretical constructions to practical instances. And we know that in theory and practice are same, but in practice they are not. So essentially, I've been trying to kind of look into these possibilities and develop suitable, implementations, which are not only supported by mathematical guarantees, but also essentially provide the much needed practical security. So in order to look into this, make and break game, we have been, we have this laboratory which we called as laboratory which we called as the Secured Embedded Architecture Lab, which have been set around 2008, and we have been looking into various aspects of make and break, attacks, and countermeasure designs. So I would also like to, on the passing, mention that this particular field is a very practical field, and therefore all the experiments that we or all the research that we do also need to be practically verified, and therefore we need to develop a proper laboratory, and we have been making a reasonably state-of-the-art laboratory where we have got instruments for performing side channel attacks, looking into the CPS security, hardware forensics, and so on. So these instruments are extremely important for putting life into our research, and also practically verifying the claims that we often would be making. So with this quick background, let me get into my talk. So my talk is divided into three parts, largely two important parts, where in the first part, I will be trying to give an overview on side channel attacks. And in the second part, I shall be trying to look into microarchitecture attacks, and finally conclude with some recent, experiments or attacks that we are working on. So to begin with, we all know that around us, there has been a tremendous growth of several technologies. And in fact, one of them are what we call as the Internet of Things, which tries to promise and extend present the internet by connecting billions of devices. So while on one hand, IoTs can really revolutionize the quality of life, however, the fact remains that often commercial IoT devices lack security measures, which can have indeed catastrophic consequences to mankind. So in the Indian context also, I would say IoTs essentially really can revolutionize the quality of life by providing us several opportunities of, starting from food control, e-governance, pharmaceuticals, and so on. But the bottom line is that they need to also integrate security into their design process. So to hit the nail, I would like to kind of draw your attention towards this paper, which is called as IoT Goes Nuclear. And this was published in IEEE Symposium on Security and Privacy, SMP, which is a flagship conference in security. And in this work, the researchers, who were largely based on Israel, they showed a very interesting attack targeting the Philips Hue lights, which are essentially smart bulbs, and they're essentially smart bulbs in the sense that you can essentially install them in your offices or in your homes. And the idea being that once you are whitelisted, you can control and command those lighting systems as per your temperament and desire. But of course, right, we do not want them to be kind of controlled and commanded by our neighbors. So now what the researchers did essentially showed by exploiting a particular feature in these lighting systems, which are called as over-the-air updates. So these embedded systems allows us or provides us this capability of doing over-the-air updates through which the firmwares can be kind of modified. However, of course, there needs to be a proper security principle to be in place, and in this case, the over-the-air update essentially is verified by a AES CCM mode, which is essentially based on advanced encryption standard, which is the de facto standard for block ciphers around the world. So the underlying key could be, say a 128-bit key. It's a 128-bit key for AES, meaning that the algorithm is reasonably mathematically secure. However, the attacker showed that by taking physical possession of a lighting system and observing the corresponding traces, in this case, the traces, when I say the traces, and I will define this more better later, the traces are essentially electromagnetic traces, which are kind of observed when these lighting systems are performing their AES CCM operation. And by a technique which is called as correlation power attack or correlation, or correlation electromagnetic attacks, they showed how they can recover the entire 128-bit key. Now, once the 128-bit key is recovered, the firmware can be modified by will, and a range of attacks can be launched. In fact, in YouTube, if you are interested, there is a very nice video of this attack where an adversary show how they take drones and fly around the the offices in which these lighting systems were installed, and they can display SOS at their will. And in the paper there are more interesting findings to show that how using this they can launch complete darkouts for a city as big as Paris. So this paper or this work kind of motivates nicely the problem that physical attacks can essentially offer very interesting attack surfaces, which are not really catered by the mathematically secured algorithms of the ciphering techniques. And using them, one can really open up very, they can really open serious attack vectors. So how can they be, stopped? So if we think that cryptography can be, alone utilized to solve this problem, then we do not really understand what cryptography is, and we do not understand the problem. Because in this case, the problem does not lie in how the algorithm was designed. So this is not really a problem in the AES algorithm, because AES remains to be a wonderful cipher, standing for the last 20 years. But at the same time, the implementation, that means the translation of the mathematical algorithm to physical instances, in this case, your embedded systems, was problematic. And we need suitable techniques to ensure that such attacks will not work on our systems. So this is if I believe that all of us are probably having some kind of device. So in this case, say a credit card device on which a crypto is executing. And imagine that when you are doing some transaction with a card accepting device secured by a nicely secured mathematical algorithm, and you're exchanging inputs and outputs. So at this point, the mathematically strong cipher will be able to protect you. However, if there is a revelation of the side channel traces or side channel information, then recovering the key is not very difficult. Luckily, all of our credit card systems are probably protected nowadays against these class of side channel attacks, showing the importance of securing and understanding such kind of attack methodologies. So this brings us to the question, what are side channels? So side channels are basically covert channels which leak information which the designers of the crypto algorithms did not consider. So it could be a, like a benign looking if-else statement, an optimization that you are probably doing in your code, whether it is a software code or it's a hardware code, which can leak information, which can leak really the secret information that you are trying to hide by the crypto algorithm. So it remains to be seen, what are the, or this motivates us to kind of look around us and see the various kinds of side channel sources in a real world system. So imagine that there is a real world system, an encryption or a decryption algorithm protected by the secret key. So as we know by our oftenly widely accepted principle, everything is known about the encryption and the decryption algorithm, but the secret key is essentially what on which the security relies. So traditionally we have been handling cryptographic algorithm, but there are various other things which are also equally important. The threat model essentially is a continuously changing process. The security goals often changes depending upon the application, the protocols on which you are applying your crypto algorithms, the implementations, which could be either the software or the hardware, the deployment and the usages, and finally the human user. So we all know that it is quite difficult to secure systems with humans in it. And there are, like people who are working at this interface also. But what I will rather, try to focus on are the software and the hardware implementations. So when we talk about software, it could be, like the timing variations. When you talk about the hardware, it could be the power consumptions, the electromagnetic radiations, the test methodologies, your fault behavior. All these can essentially reveal information and open new, like Pandora's box for a side channel attacker. So now let us try to look at one of the most traditional form of side channel attacks, and these are called as, like power-based side channel attacks. So on this particular slide, I try to show you how a power trace, or this could be even an electromagnetic trace of an AES engine would look like. So we know that, if I talk about the AES 128 in particular, so AES 128 is a version of the AES algorithm which works on a 128-bit secret key. So now we can observe, in this particular trace, there are 10, like very regular patterns, and these regular patterns correspond to the 10 rounds of the AES operation. If you zoom into one of the rounds on the right-hand side, you can see more variations which are pertaining to the underlying operations of the AES algorithm. So these class of attacks, which tries to kind of exploit the operation dependence of power, are largely called as simple power attacks, or SPA. Now there is an even more powerful form of attack, which are called as differential power attacks, which tries to exploit the variations of power consumption or electromagnetic radiations because of the underlying data. So you can imagine that these attacks are even more strong than the SPA or simple power attacks. And even if there is an implementation which is protected against SPA, can be vulnerable against DPA or differential power attacks. So these works, or these kind of, like definitions, were originally proposed in this very classical paper from Paul Kocher and his team in Crypto 99. So we will try to take a look at one of these attack vectors. In particular, like I thought of, like talking about, the CPA attack. This is the same attack that was kind of applied in in the paper that I just referred in IEEE Assembly. So let us try to take a quick look at how this attack works. So the AES algorithm, essentially, or AES 128 algorithm, being more specific, takes the plain text and kind of, like sees it as a 16 byte. So you can see here, it is arranged as a 4x4 square. It shows how the plain text or the input to the cipher is arranged. And likewise, the corresponding key is also arranged in a similar manner. That means it is arranged in a 4x4 grid where every element is a byte. So now, if you take, like several inputs or several plain text, as we call in terminology of crypto, they take it and, like encrypt using the key. The key is kind of remains constant across these encryptions, and it produces various cipher texts. So these, attack techniques or analysis technique can be also explained both from the plain text side, that means both from the input side, as well as from the output or the cipher text side. So let us try to take, explain this or understand this from the side of the plain text. So these attacks are based on divide and conquer attack, which means that even if we have got a 128-bit key, you do not try to recover the entire 128-bit key at once, but rather you focus on only one byte of this. So let us say, like this is the byte that you are interested to recover. So this byte in particular kind of interacts with one of the bytes of the plain text. And if we denote X to be that byte of the plain text and K to be the corresponding byte of the key, the interaction often is done by XORing between them and then applying a nonlinear transformation, which is called as the S box. So now this gives rise to an intermediate data. Now, what the attacker tries to do is the attacker tries to kind of guess this possible key byte and note that this is only a byte, and therefore this byte can take 256 values, and like observes the intermediate values of which are basically the output of this S box. So now you can see that if the key is kind of varied, that means if I take all the possible 256 possible values of this intermediate key byte, then this S box can also give rise to like 256 values. For each of these values, I apply something which is called as a powered model. So these powered models are nothing but very popular models in the VLSI or very large integrated, very large scale integrated community, which tries to kind of, analyze or model the dynamic power consumed by the device based upon very simple models. So in this case, let us take a very simple model, and we can of course go into more complicated models. But just to kind of explain the idea, I will take a very simple model. So the simple model is basically the Hamming weight of the byte, which corresponds to the number of ones in the corresponding byte. And based upon this, right, note that this S of X XOR K is a byte, and therefore I just note the number of ones in that byte, and that gives me something which is called as the hypothetical power. So this hypothetical power is called hypothetical because it essentially relies upon the hypothesis that I set for the key. So note that, of course, right, I mean, I'm not sure at this point which of the hypothesis is correct, because out of the 256 values, only one of the values will be correct. In order to do that, I also observe the side channel trace. So this side channel trace is the trace that I just now showed to you, like it's a power variation. And now what I do is, for every key hypothesis that I do, I apply this hypothesis. So suppose I fix the key hypothesis to some value, okay, say K0, and I do this operation for all the possible plain text that I have. So let us say, like I've got 1,000 plain text. For all of these 1,000 plain text, I obtain this intermediate byte, apply my hypothetical powered model, and I also observe the corresponding side channel trace that I have accumulated. And then I perform a very simple statistical analysis, which is, say, the correlation. So I basically correlate, like these hypothetical power values with the observed power values. And I do this for all the possible key hypotheses that I essentially will need to handle. So in this case, for AES, suppose I'm talking about a byte. So there are 256 possible values of the key hypothesis. Among the key hypotheses, I essentially return that key which maximizes this correlation as the possible candidate key. So this process I would repeat for all the possible key bytes that I have got. And therefore, we can easily see that this attack, being a divide and conquer attack, it will not really be thwarted by increasing the key size. And in fact, right, in this case, the complexity would be something which is proportional to 2 power of 8. And therefore, it is a drastic reduction of the possible key space. So this is a very simplistic illustration. Of course, we need to handle the noise and other things, which will probably make this attack a bit more complicated. But this remains the underlying principle or technique of performing, differential power attacks. And here is a very simple illustration of our simulation result of a CPA, which has been done on a 10th round AES. You can see that on the x-axis of this particular graph, we show with the traces how the correlation essentially varies for the correct key candidate byte and is compared with the other ones which are wrong. So you can easily see that the correct key hypothesis has got a very, like a remarkably different correlation compared to the other ones, and therefore they can be distinguished. If there is noise, then of course the separation diminishes, but nonetheless it can still be distinguished. So this is a very, like one of the, as I said, that is this kind of summarizes the working principle of what we call as correlation power attacks, or in general, power-based side channel attacks. So after this, I will try to talk about, of course, like there are many other, attack vectors or many other interpretations of, side channel attacks. There are many versions of side channel attacks in the profile setting and in the non-profile setting. The one that I just described is a side channel attack in, in the non-profile setting, because I do not really have any profiling phase. Scientists have also tried to look at this from the information theoretic point of view. So what I mean by that is, from the information theoretic point of view, we can also, explain this by, as shown over here. So you can see that there is an input which is shown over X, which is basically the input means the plain text to the cipher, and is processed by the IC, which is essentially hosting your crypto algorithm. Then, as I just now said, this input gets modified by the secret key, which is, say, embedded or stored in some kind of non-volatile memory in the IC, and it produces some intermediate result. And this intermediate result essentially is supposed to be depicted here as channel 1. That means the transformation from the input to this intermediate data is one channel. whereas the, like transformation from that intermediate data to the observable, where you are, like observing, you have got your measurement set up and you're observing, say, the power traces, for example, or maybe the electromagnetic traces in other instances, and this gives you the other channel. Okay, and now what I can do is I have got my output observable, and what I can do is I can try to kind of, have some kind of intermediate. So I can take various X values or various input values, and I can, organize these or distribute these input X values into leakage bins as shown over here. So these leakage bins are shown over here as different classes, and these classes could correspond to the Hamming value of your intermediate data. As I mentioned that, the intermediate data is, say, S of X XOR K, right? I mean, this is the intermediate data that you have. And this intermediate data is the corresponding Hamming weight of this S of X XOR K essentially gives you these, leakage bins. And now what you can do is you can essentially try to kind of compute the, certain probability distributions. So these probability distributions, are nothing but the probability that the output is, or the observable is, say, some specific value of O. And you can also calculate the conditional probability distribution, which means given the leakage bin, what is the probability that you have got a certain observable. And now using this, you can essentially try to find out the mutual information between your observable O and the leakage. Now note that this leakage essentially depended upon the value of the K, because when I am calculating, the intermediate data, I have this term of K, right, which is essentially my key hypothesis. So therefore, right, I will try to find out all the possible key values and the corresponding mutual information, and then return that key as the correct key, which maximizes this mutual information. And this leaks the key. So this can be one way of explaining, from an information theoretic point of view, how side channel works. And people have shown that asymptotically, all the statistical attacks that we do are kind of equivalent in terms of their success rate and in terms of their efficiency. So moving over, there are, as I mentioned, that there are various other techniques of side channel attacks. So along with power-based side channel attack, the other very important class of side channel attacks are what are called as fault-based cryptanalysis. So in fault-based cryptanalysis, the idea is that what we try to do is often we take a plain text, we perform an encryption, we obtain a fault-free cipher. In another run of the execution, when we want to kind of obtain the output, say the cipher in this case, we do a fault induction. Now, the fault induction can be done by various means. In our laboratory, we have got setups of doing it by clock glitches, by EM-based fault injections, or laser-based fault injection. But the question that I would try to kind of address here is that what do you do with this fault, or why does this fault really leak the secret key? So in order to understand this, let us try to consider again the AES algorithm. So imagine that, and in particular, I'm trying to look at the last few rounds of the AES 128 algorithm. So imagine that there is a fault that has been created by these various techniques, or whether by these various methods that I just now mentioned. Now the fault is completely unknown. I have got no control on the fault, but I essentially can fairly accurately, do some, techniques through which I can create a fault. But if I assume even, that I don't have any control of the fault, and I allow the fault to propagate because of the various structure of the AES algorithm, beyond a point as shown here in this particular, where I highlight it, you can see that the faults start behaving in a manner where they manifest interrelationships. For example, you can see here in this particular column that I highlight, the first fault value is twice the fault value than the other one. Of course, this twice is in some mathematical, field and other things. But even if we ignore them, they essentially have some kind of interrelationships, right? And now if you go down further, you will find out more interrelationships as shown here after a point. So now what the attacker tries to do is the attacker tries to guess the key, and tries to kind of go back this ciphering process and try to see that whether really these interrelationships are maintained. All those keys which do not maintain these interrelationships are rejected and removed from the and filtered out from the key space. So this way, you can essentially perform very efficient attacks. And in fact, our research shows that even for AES 128, which is the world de facto standard for block ciphers, a single fault can reduce the key size from 2 power of 128 to a paltry 2 to the power of 8 values, in a time complexity which is like 2 to the power of 30 AES encryptions. Now, on a reasonable computer, you can essentially simulate this in something like 15 to 30 minutes. So this shows that how a single fault attack can be quite powerful even for ciphers like AES. And although this attack we found out around 2010, 11 or so, recently this has made an impact, or I would say a more has hit the news by this famous attack which is called as Plunderbolt, which was launched against Intel SGX. And in fact, because the way of underlying the way the fault was induced by exploiting what is called as a voltage frequency scaling. This is an artifact that is there in modern day computer architectures. The objective is to kind of do a proper amount of power management in the computer systems. But the same ability can also be misused by the attackers to launch faults, and then subsequently these faults can be exploited and analyzed in the way that I just now mentioned. And it shows that a single fault essentially can be, since the single fault can be quite catastrophic, eventually, these systems are not secured. And in fact, Intel ended up in kind of, deprecating these systems from the 11th generation processors, showing or, also echoing the point that these are very serious forms of adversaries. So you can, if you're interested, you can look at this IEEE security and privacy paper, which is called as Plunderbolt, how a little bit of undervolting can really create a lot of trouble. There is also a GitHub, repository which shows how the fault attack works using a single fault for AES. So moving ahead, as we know that these class of attacks are very serious, we need to develop suitable fault-tolerant architectures. There are, various kinds of fault attack countermeasures that have been developed. There are some which are, follow the classical methodology or classical fault-tolerant techniques, which are called as detection-based countermeasures, which means that you do a fault, you repeat the process, and then you check. So this could be, redundancy by the hardware level. It could be redundancy at the timing level. There are also some others which are, in redundancy at the information level, which are called as parity and using other error correction codes. But researchers have shown that because of the fact that many of these faults are often biased and they are not really, complete random process, as we often would probably anticipate in a classical fault tolerance scenario, they can often be bypassed. So researchers have also developed other more complicated forms of countermeasures, which are called as infective countermeasures, which by the algorithm tries to kind of infect and pollute the faults in a manner so that they are not exploitable. But they have also been, targeted by more clever adversaries, and therefore the kind of, a big problem remains is that when you have got a countermeasure, how do you really test that whether your countermeasure is secure or not? So in DAC 2019, we try to come up with a technique through which we essentially can guarantee or, at least understand whether your fault countermeasure is leaking. So in this countermeasure, in a very simple sense, what we do is we do fault simulations by different values of the faults, and then try to play around with the distribution that the output is manifesting. The idea being that if the distributions are distinguishable, then it basically, is popping out information about the fault and equivalently about the secret key. So in one of our recent works, of course, you can, mathematically formulate this. And the idea of, these kind of conditions are basically to guarantee that the output differential that you're observing is not leaking any information about the fault or about the key. So how do you really, test it and develop a complete end-to-end framework for doing that? So the idea that we are trying to kind of envisage here is that you take a crypto system and you perform fault simulations. So in this case, let me take, two instances of faults, F0 and F1, and which results in ciphertext. So now you take this, data set and you try to kind of train a machine learning model, in this case, a deep learning framework, and you ask the deep learning framework to essentially guess which was the fault instance, whether it was the fault instance F0 or whether the fault instance was F1. Note that if the neural network architecture is not able to learn from a probability which is around 0.5, then that means that you are good. Otherwise, if you are able to kind of observe, an accuracy which is significantly deviant from 0.5, either on the plus side or on the negative side, it means that the output distribution is revealing information about the fault, and this can be kind of categorized as a leakage. So using this very simple framework, we were able to kind of detect leakages in, like both detection countermeasures and effective countermeasures, showing the prowess of this methodology. So we are currently working on developing an end-to-end framework, which we called as ESP Anveshwak. ESP is one of our, like incubations out of our lab, to which we try to kind of, like develop an end-to-end system for, like side channel evaluation. So let me try to, like quickly take you through a tour of side channel attack in our laboratory. I hope that this system is working. So. So that's the, like an overview on, like some of the basics on sidechain attacks. And I move ahead and get into my next part, which is on microarchitecture attacks. So in this particular, the first part of my talk, I've been largely dealing with power attacks and fault attacks, which often are more threatening for embedded systems. But what happens is, like when you try to kind of also target more, like standard computing systems, like maybe desktops, laptops, or other, like computing devices. So in this case, what essentially remains to be kind of looked into is that, like the microarchitectural exploits, which often are, like stem from your underlying computer architecture. So we probably have come across these words like meltdown and specter, which is essentially shook the world and showed that how serious can they be, against various computing devices. So in this case, right, I mean, for specter and meltdown, they tried to exploit a very, a deep-rooted feature in modern-day computing systems, which are called as speculative executions. So now, even if you, 20 years down the line, if you're able to kind of understand these attack vectors and you try to fix them, then you would probably, require a patch that can result in a major performance hit, or we have to kind of go back our evolution for 20 years. And that really can be quite costly, at the same time, quite surprising that we took so much time to understand and unearth such kind of attack vectors. So therefore, it is important to mind this gap and try to develop a holistic approach for building secure systems, which are not only, concerned about the performance of the of your computing devices, but also, aware of the leakage that can probably crop up because of your underlying computer architecture. So therefore, I will try to talk about, one of our, experiences with an old research work, which we did along with Entity Labs in Japan, which were, so this result you can find out in this paper published at IndoCrypt in 2009. And it tries to look at, timing attacks on block ciphers, just like the cipher that we just now described as AES. So in particular, I will try to focus on one specific form of sidechain attack, which are called as cache-based sidechain attacks. These are quite relevant for not only your standard desktops, but also even on modern day embedded devices. And I will try to kind of look into, in particular, this attack vector. Of course, there are several other attack vectors which are also important, like branch prediction attacks, or attacks which are based on hyper-threading attacks which target the memory. But in this particular discussion, right, we will try to focus on the cache architecture. So we know that cache is a fast form of memory which sits in between your microprocessor and the main memory, trying to bridge the memory wall. The idea being is that if there is a cache hit, that means if you're able to get your data in the cache memory, then the access time is less, the power consumption is less. On the other hand, right, if there is a cache miss, then the access time is more, and there are more data manipulations that need to be done. And therefore, if there is an astute adversary who is able to observe and distinguish between a cache hit and a cache miss, then what really can it do? So that is essentially the objective of cache-based adversaries. So to explain this, let me take this, example of a table-based AES implementation or table-based cipher implementation. So note that when you want to go into software designs of ciphering algorithms, often they are implemented by lookup tables to make them fast. And in fact, right, if you look at OpenASL, which is very, like a standard distribution of crypto libraries, you will find that AES has been implemented using certain tables, which are called as T tables. So now let us try to take a look at, two parts of a cipher. Without loss of generality are denoted as P0 and P4. And imagine that they both essentially are operating on, certain tables. So in one case, right, suppose imagine that, this is a key that essentially is shown here as K0. And there is another key which is shown here as K4. And therefore, the access that you are doing in first table is P0 XORed with K0. And for the second one, it is the XOR of P4 and K4. So now when you are making these table accesses, right, I mean, the idea is that both these K0 and K4 are independent. And therefore, right, even if I give you information about K0, you should not leak any information about K4. Okay, so if you consider them to be, say, two parts of the AES ciphering key, then both of them are two distinct bytes. K0 is a byte, K4 is another byte. And therefore, the entropy of K0 and K4 should be ideally corresponding to 16 bits of information. However, imagine that there is a cache hit and the adversary is able to observe that by observing this timing channel and seeing that the time is lesser than a threshold, and therefore suspecting that the access to P4 XORed with K4 is a result of a cache hit with for the corresponding address that was was corresponding to the XOR of P0 and K0. It immediately means that one can form equations of this nature. That means P0 XOR with K0 is equal to P4 XOR with K4. Of course, right, if the cache line has got more number of bytes, it will not be exactly equal, but it will be kind of equivalent. So this means that now we can essentially form relationships between K0 and K4. Now, if I give you information about K0, you can calculate K4, and therefore the overall entropy of K0 and K4 together reduces. So the moment we know that there is a reduction in entropy, we believe that there is a possibility of an attack. Even if there is a cache miss, you can essentially exclude certain cases, and therefore that also leads to a certain amount of leakage of information. So there was a very famous paper again by Osvik, Shamir, and Tromar, where they showed how we can perform certain attacks which are called as cache access attacks. So these attacks, which are often called as prime and probe attacks, are a very powerful form of attacks, which are more prevalent nowadays when we talk about cloud computing and so on, where the attacker, which is say like a spy process, and the victim, say, which is an AES process, are co-deciding and working on the same hardware. Imagine that the spy comes in and fills the cache with some garbage data, and now when the handler gets back to the AES essentially performs its encryption, and there is a distinct footprint. And since the cache is kind of shared, essentially it leads to kind of removing certain amount of information from the spy. And now when the spy comes in, it can use its timing channel and understand which ones where the cache misses and which one where the cache hits. So this means that the spy is able to observe the footprint of the dimension. So this leads to a reduction of the total key space, and in the worst case, right, it can lead to very efficient attacks against the AES, or even AES or any other cipher for that matter. So there was another form of cache attack which was also very popular, which was due to Dan Bernstein in 2005. These attacks were even more popular because they were kind of trying to attack a remote server. Imagine that there is a remote server which is running an encryption software, and there is a remote attacker who is not only sending data for encryption, but is also observing the timing channel and is accumulating statistics. So now how in Bernstein's attack, they again take AES 120 as an example, and suppose, right, they focus on one of the bytes of this encryption process shown here as this P0 byte, and for the other parts they are randomly varied. So what I do is I take a specific value of P0, say 00 to begin with, and I give random variations to the other 15 bytes. I observe the timing information, and I observe the average timing that is required. And I do this for all possible values of P0. P0 can range from 0 to 255. I do this and I observe this characteristic, which I called as the timing characteristic. Now, the interesting part is that if you do this for, say, the all 0 keys, and if you repeat this experiment with an unknown key, you will find out this pattern is kind of consistent. And you can, if you are observing, right, you can see here that there are certain patterns which kind of are similar, and there is only a shift in the corresponding locations over there. Now, if you measure this shift and if you correlate these two traces, you can essentially reveal and obtain the amount of the secret key, and therefore, right, it shows that you can follow it up by an analysis to obtain the corresponding secret key. So these attacks are quite prevalent for for crypto systems or crypto libraries, particularly those which are implemented using lookup tables. So here is an example of how the software implementation of AES in OpenSSL library looks like. It is implemented using 4 tables, each of them being 1 kilobytes. So these attacks are perfectly possible on such kind of systems. And I would like to mention on the passing that nowadays we have got a very nice instruction called AES-NI, where for Intel-based systems, and likewise there are also for other processor vendors. But the fact remains is that, well, AES can be probably protected against such class of attacks, but every day, right, there are so many crypto algorithms which are being developed. It is not possible often, to provide dedicated instructions for all of them. And therefore, right, this still remains a wide concern. So getting back to our AES target with 4 kilobyte implementation, why does this attack work? So if you observe and plot the number of misses and observe the frequency number of the number of misses, you can see that there is a very nice distribution, and we believe that the cache attacks are possible because of this distribution. And in fact, it is not very difficult to take 2 encryptions, call it E1 and E2, and find out what is the difference of time of E1 and time of E2. So if you use very classical equations like which are there in, like to predict the timing for a cache-based system, you can show that this difference of timing is proportional to the number of cache misses. And because the number of cache misses vary nicely, the timing also varies, and that can be exploited by adversaries. So one important concern was, if I implement the AES using small tables, say a 256 byte table, will the attack still work? And you can show that, when your table size is small, then the number of cache misses becomes roughly a constant, and therefore it was widely believed that cache attacks are more difficult. So, and in fact, right, if you observe the timing behavior, you will see that with small tables, the variations are much smaller compared to larger tables, and therefore it was believed that the cache attacks are difficult. So in particular, in this work, we show that you can still circumvent them and you can still attack them by exploiting some modern day features in your computing systems. In particular, in the current day processors, there are many features like speculative loading, prefetching, out of order loading, parallelizations, overlapping, and so on. And we try to kind of look into them in the context of a block cipher. So in the block cipher, you have got various rounds of encryption. So if we talk about AES, and talk about the S box of AES, in the first round, there are, say, 16 S boxes. Likewise, in the second round, there are 16 S boxes. While in the first round, the S boxes are independent, there is a dependence between the rounds. Like you can show that round 2 S boxes, you cannot perform until unless the first round S boxes are completed. Now, what has got that to do with the timing of your ciphering? So we can show here that out of order loading, you can essentially perform inside the round, but you cannot do it across the round. And therefore, right, even if in your modern day computing systems, you have got facilities of handling cache misses in parallel in an out of order manner, you can do that in one of the rounds. That means you can do it intra round, but you cannot do them inter round because of these dependencies. So now, if I take two examples, something that will be probably corresponding to your small cipher implementation, where the number of cache misses are roughly a constant, there the number of cache misses is not only important, but the distribution of the cache misses is also equally important. So for example, if I take, for example, the first, like instance E1 and the second instance E2, you can see that in the first instance E1, the cache misses are shown here as 2 plus 1 plus 1, whereas in the second instance, right, it is like 1 misses nicely distributed across the rounds. Now, which one of E1 and E2 would essentially take the same amount of time? So in a classical sense, both have got the same number of misses. So I would expect that both of them will take the same amount of time. But because of the fact that out of order loading essentially can handle these two cache misses in parallel, what will probably happen in a real life scenario, the timing for E1 will be lesser than the timing of E2. And this was very, very popular, very prevalent in the computing system that we were working on at 2010, 2011, and so on. And therefore, right, we can really, like still launch attacks. In particular, we try to look into other artifacts like, like what are called as hardware prefetches. The hardware prefetches are artifacts in your cache memory, which tries to bring data before they're accessed. And that also creates, like very interesting distributions, which can be exploited and observed. And in this paper in Journal of Cryptology in 2021, we try to analyze various kinds of prefetching techniques and explain how the timing characteristic that I showed in Bernstein's experiment can be kind of, like modeled and also kind of experimented with. So therefore, the fact remains that in modern day caches, the execution time not only depends upon the number of misses, but also on the distribution of misses. The cache prefetches also have got, like a role to play. And because of this, right, the cache remains fundamentally insecure. And in our work, we showed that if you take a cipher, like very standard cipher, a 128-bit cipher, which was called as Clepia, it was designed by Sony Corporation, and we showed that in an attack which takes around 300 seconds, one can recover the entire key. Interestingly, we could make the attack work on modern day systems at that time of writing our paper, like Pentium 4, Intel Atom, Xeon Core 2 servers, but the attack failed on Pentium 3. So we believe that one of the reasons why this attack failed was because of the, like absence of these modern day artifacts. So this work also probably nicely brings out this point that while it is important to kind of develop and evolve in your computing systems or computer architecture, but they also need to be kind of kept in mind along with the security leakages. So I think I'm running out of time. I'll just quickly talk about in the third part about some very recent sidechain attack that we have been working on. So this attack we called as Wrestle, which basically means wrestle. So this is a paper that we published in Chess in 2021, where we show how a combination of two artifacts, one of them is a processor hardware, unit, which is called as a return address stack, abbreviated as RAS, along with a scheduling technique, which is called as deadline scheduler in the OS or in the operating system, can be kind of targeted together and lead to very interesting attacks against ECDSA, which is an elliptic curve digital signature algorithm. So in this particular, just to quickly kind of bring the context of the deadline scheduler, deadline schedulers are very popular forms of scheduling techniques, particularly suited for real-time operating systems and so on, where you can essentially, fix certain parameters like the scheduling runtime, the period, and the scheduling deadline using CAPSYS privilege, which means you do not need root privilege or super user privilege to adjust them. Now, the idea is that once, of course, like you can do it for your own process, but the fact that you can do it for your own process can also have an impact on the victim process. And this is something that was not really studied so much, and this is something that we looked into along with this other artifact, which is called the return address stack. So the return address stack is a very simple hardware stack, which is often present in your computing systems. And the objective of this is to handle the return addresses and ensure that the branches that so the branch misses are reduced in this context. So we all know that in our computing systems, we have got branch prediction techniques. And the objective of the branch prediction techniques is to reduce the branch misses. And it is also kind of a very popular, I would say thumb rule in writing crypto libraries, where you try to write the branches in a manner so that they don't leak information. But we try to look at this special class of branch statements, which are called as return statements. So note that the same function can be called from different locations in your memory. And therefore, if you are using traditional branch prediction techniques, then it can lead to a large amount of branch misses. And because of, you want to kind of alleviate this, modern day computing systems have this hardware stack, which is called the return address stack, which is a small stack, which tries to handle, these branch misses. So you can see here, this shows how this particular slide shows you a RAS state. The first return address, when you have got a return, the corresponding return address is stored in the return address stack. Okay, and if you are going down and down, the corresponding return addresses are pushed into the stack. And once you get out of that, and when you return, your stack is popped. Now, I would like to mention that this is not the same as your software stack. So it's a separate, dedicated hardware stack that your computer architecture maintains. So now what you can do, interestingly, as an attacker, you can essentially perform nesting of the stack. The objective of doing this nesting is to completely fill up the return address stack, which is usually something which is not very big. So in our experiment, we found out that the architectures that we were trying to work on were having something like a size of 16. And we essentially created a complete overflow of the stack. The objective being is that the moment there is a 17th return, function call that has been done, it will essentially put that into the stack, and therefore one of the stacks, there will be an underflow in the stack, and that will essentially lead to, the moment that you don't find that return address being in the stack, you will resort, or the system will resort to its traditional branch prediction techniques, and that will lead to a branch miss, and that will essentially reflect by an increase in the time. And in fact, our experiments, we showed that, if you have got, say, 16 or 17 function call, so while the previous function calls will have small amount of time, because if the system is able to get the return address from the stack, the moment there is an underflow, there is an increase in the time, because your data is not available in the stack, and therefore this will lead to a branch miss. So now, how do you really exploit them? So we do this in two processes. The first is by showing a covert channel. So covert channels are very important because from the adversary point of view, because many systems, try to kind of, give guarantees of separation between various compartments, but the establishment of a covert channel means that the isolation fails. So in our case, like in this kind of channels, what we have is a transmitter, and then there is a corresponding receiver. So you can see here that we show how a transmitter works along with the receiver. The transmitter, using the covert channel, wants to transmit a 0-1 sequence. In this case, this is the corresponding 0-1 sequence that you would like to kind of transmit without anybody being able to observe here, because you are not sending any information explicitly over the channel. So what we do is that the transmitter fills up the stack just as I mentioned, and it waits for the and the idea is that once the stack is filled up, okay, I mean the fact that whether the transmitter makes an additional function call or it doesn't make an additional function call can be also understood and perceived by the receiver by observing the timing channel. If there is an increase in the timing information, then it means that the transmitter is making this additional function call, else it is not making that function call. So therefore, right, what we do is we set the transmitter in a manner where the 0, 1 value that I would like to kind of, communicate, I use that as a control channel of whether I call a function or I don't call a function. And that means that when the attacker, when the receiver is observing the timing channel, it gets an indirect information about the 0, 1 sequence. So in fact, right, we showed that you can quite accurately communicate this information over channels which are not well established, and therefore they are called as covert channels. Interestingly, you can also use these attacks to launch attacks on the elliptic curve digital signature algorithm. So I would like to mention that ECDSA is a very standard form of signing algorithm, but for all these signature generations, there is something which is called as a nonce. And every time you essentially develop a new signing, a new nonce is generated, and that is used in the signing process. So as an attacker, you have got a very small attack margin because you need to observe the nonce, the timing channel, and get information about the nonce, and then you can use it along with your some other techniques to essentially recover the corresponding signing key. So what we do here is we targeted a very standard curve, which is called as P256. And rather than trying to observe the entire nonce, because that is difficult, we tried to observe some bits of the nonce. In particular, we tried to observe, say, 5 bits of the nonce. And then what the spy does is the spy sets up the stack, as I mentioned, and then it allows the victim process to run. The victim process in this case is the signature scheme. Now, the deadline scheduler is exploited and manipulated in a manner so that there is a nice handshake between the victim process and the spy process, allowing the spy process timing granularity, which it can try to exploit. In particular, we showed that how, so these are some experiments that we ran on our systems, and we showed that how, some bits of the, it's actually 6 MSBs of the nonce can be recovered. And after this nonce partially can be recovered, there is a very nice technique, which I will not go in details, which is based on lattice reduction, which essentially can be followed up. And in less than 1 hour, one can recover the entire signature key. So I would like to conclude now. I think I'm running out of time. I mean, side channels expose a very strong gap between theory and practice. Microarchitecture attacks encompass the intersection of architecture and computer security. And while there has been a tremendous development of computing systems, but often they have been developed without taking care of security, and that essentially has also hit major computer architecture vendors. In fact, Intel stock fell down by a significant percentage after the revelation of Spectre and Meltdown. This shows that design for security, along with other objectives, is actually an important, criteria for designing systems. So it's a good time to think about a clean paper pencil design with RISC-V around us. And to echo the words of famous Hennessy and Patterson, it seems that security is a good topic to look into, in particular in conjunction with computer architecture. So before I conclude, I would like to briefly advertise, this conference that we annually organize in India. So this we call as Security, Privacy, and Applied Crypto Engineering, abbreviated as SPACE. This year it will be in Rajasthan in December. So some of you are interested to participate. The deadline is around September 1. You are most welcome to participate. So here are some textbooks that we wrote on hardware security and timing channels in cryptography and fault tolerance in cryptography. So there is also an open, online course that we run on hardware security. You are most welcome if you're interested. So before I conclude, I mean, taking this famous word of every contact leaves a trace. Our observation is that every computation leaves a trace, and that essentially opens up very interesting, avenues of research, both from the attack point of view as well as from the countermeasure design point of view. So with this, I would like to say thank you. If there are any questions, I would be very happy to address.
Thank you, Professor Debdeep, for the engaging talk. We can take few questions now.
Okay, so I don't see any questions in the chat. but if there is something, I would be happy to address.
Professor, I had a question regarding the power analysis. So that assumes that you have component level access, right? Like if you measure the power signature at the power module level, that would be filtered through multiple capacitor filters, right?
Yeah. So this the power measurement that we are doing is at the SoC level. So it is the I mean, it's not only that we are targeting and observing the power of only the crypto module, but it's a kind of combination of the entire SoC. So there are there are a lot of components we are actually adding on to the noise of the power consumption. Okay.
So the waveform observed is a superposition of multiple.
Right. So that means that your techniques, right, should also have capabilities of handling that noise, right? Essentially, which comes from the various systems, basically.
Right. So is an attacker able to isolate the noise and figure out?
So the thing is that why these attacks even work even in spite of noise is because by the nature of this, the definition of these attacks, right, it basically tries to treat the other components which are not statistically related to the key as independent process actually. So if you observe even in the block cipher, right, I mean that we were showing our example on, we were targeting one S box or one part of the key, right? So the other parts of the key are independent of this particular key. So they are also adding on noise. In fact, we call them as algorithmic noise. Okay. Now, the other things that you are talking about are electrical noise. So they are also will be handled in a similar fashion. So our observation shows that with more noise, right, it will probably make the attack a bit more hard, but it will not rule out the attack. So it will probably, increase in a linear fashion. And eventually, right, we will still be able to distinguish the correct key from the wrong ones.
Thank you.
And there are many other methods that also have been developed nowadays. Like I was talking about the classical correlation power attack. In fact, people have been applying, like deep learning techniques, which are really powerful and, like in certain settings can recover the key in probably less than 50 traces actually. Any other question?
Professor, we would like to thank you again for being a part of the seminar series.
Thank you. It was a pleasure.
As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details, and the links have already been pasted in the chat box. Thank you, everyone, and have a great evening.